Hi, Les Hall again, making my 7th YouTube video on inventions. This time we're going to talk about something I created in 2007 called the Boolean Sequencer. It's a music invention for synthesizers. Before we get into that, I want to mention a word about invention and reinvention. What I personally call reinvention. It turns out that the vast majority of inventions are what I call reinventions because the base idea already exists. People say, don't reinvent the wheel. Well, I got news for those people. If we never reinvented the wheel, we'd still be using wooden wagon wheels on our cars. Okay, there are teams of engineers around the world continuously reinventing the wheel. To this day, it passed the year 2000. Okay, so reinvention is important. The vast majority of patents, as I mentioned, are reinventions. Well, the Boolean sequencer is a reinvention. I created it all by myself. Like so many reinventions, they are reimagined from scratch. And then I evangelized it all around electromusic.com, electro-music.com, till my friends got sick of hearing about it. But I was excited about it and still am today. What, 6 years later, 5 years later? Then later I myself found evidence that it existed in a previous state, in a simpler form, more primitive form, more basic form, but it exists throughout our culture in music. The very early synthesizers, when they first had digital logic to work with, they wired it up and said, this thing makes sound. Makes interesting sound. Let's make a song with it. And then they forgot about it or didn't categorize it as a thing, a reinvention or an invention. And just went through history like that. And I even found buddies of mine doing Boolean sequencer type things to their other kind of sequencers. So it's an idea that comes naturally. But what I did is I gave it a name, Boolean sequencer, or BS for fun. Silly name, silly acronym. And I experimented with it. I tried all kind of variations, many, like a dozen variations of it. You can build it any way you want. So let's get into what it is. It starts with a clock. A clock is a square wave signal that goes tick, 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 tick. Let me get to the camera. Square wave is low, and then logic high. Low, and then logic high. And each of those pulses represents a note, a single note in the music. So we're talking about tempo rate clock. Okay, so you got this clock, you got a square wave oscillator, you dial it up, little dial it up to the right frequency, however many beats per minute you want, and you get your tempo. Put that into a divider, usually a binary divider, also known as a counter chip. I prefer the CD4040 counter chip, the CMOS, the classic CMOS, and CMOS is pronounced like moss from the sea, but it actually is an acronym, CMOS, complementary metal oxide semiconductor, referring to the electrical nature of the base circuits that make it up. CMOS is old as dirt, originated in the 70s, I think. Didn't get popular until the 80s when the patents ran out or something like that. I don't know the history. But it's been around as long as I have, just about. Professionally at least. And we still work with CMOS today a lot in electromusic.com. It's still popular. Your computer's processor is made of CMOS. CMOS ain't going away. There's super duper duper CMOS today. They've been working on it a long time. They really got it refined. But the old style logic chips are what I'm talking about. Very simple chips you can buy for 50 cents or a few dollars each at most. CD4040 is your counter. You put your clock in it. Tie the reset low. I believe it's an active high reset. I forget. And you get 12 output pins. Plus the clock being the least significant bit, you actually get 13 bits of binary count. That is 8K. So you have, it starts at 0 and it goes up to 8,000 some odd and rolls back to 0. In binary, you know, one, I'm not even going to count binary. I forgot. That's embarrassing. Let's see. 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, I can still do it. Alright. But this thing counts at tempo rate all the way up to 1,000. 8,000 rolls over. Okay, you got your counter. Now you tap off as many bits, any combination of bits you want coming out of that counter, and you feed them into a cloud of logic. A cloud of logic. We call it a cloud of logic because it's any combination of logic gates and hooked up any which way you choose. You can be creative. You can say, I want to work with XOR gates, exclusive OR, because they sound cool to me. And if you make a Boolean sequencer out of exclusive OR gates, or exclusive NOR gates, you will get continuous variation of the notes. If you make it out of AND or NAND gates, you will get pauses between the notes, sometimes long pauses, often short pauses, which can be dramatic and interesting. If you make it out of OR or NOR gates, you will get, if I recall correctly, doing that, you will get continuous sound with long, sustained notes. And then you can mix and match those. So you can do whatever you want. So you hook up a cloud of logic which has one or more outputs. Okay, say we have 3 outputs. Okay. What we want out of this network is a CV, a control voltage, a single analog stepped voltage that comes along and says, I want to be this note. And then the clock ticks up, I want to be, this note. And then the clock ticks and it says, I'm going to be this note, and then this note, and then this note. You get the idea? It's a staircase. It's a stepped voltage. Okay, we're getting there. How do we do this? We use an aggregator, an aggregation network, typically a combination of resistors. The simplest way to do it is just put a resistor, a 100K resistor or a 10K resistor, something like that, in that ballpark, whatever you got, in series with each of the logic outputs. Then tie the other end of those resistors together. It makes a sort of a voltage divider thing. You can choose different resistor values to give different weightings to each of the outputs. You can also use a thing like R2R ladder, combination of it, hook up some potentiometers to be able to vary it. You can experiment, you can do all kinds of things. But somehow hook them up the simplest way, resistors in series. Now you got your control voltage, but it's a high impedance control voltage. You don't want to send that thing over noisy wires to your other equipment. You don't know what your equipment load characteristics might be, etc., etc. Electrically speaking, we need an analog buffer. So we use a voltage follower. A voltage follower is an op-amp circuit. You buy an op-amp chip. You put 3 wires on it, power, ground, and feedback from the output to the minus input. Then you take the input, hook it up to the plus input, take the output and send it on its journey through to the world. Typically, the termination on a modular synthesizer that you want to use is a 2.2K resistor in series with the output and a nice big juicy electrolytic capacitor in series with that, with the minus side connected to the very final output and the plus side connected to the resistor. And a big and juicy cap, I would say 22 microfarads, 100 microfarads, 10 microfarads, whatever, however big you can afford to do it, with space constraints and whatnot, what do you have in stock. And this, it's not critical, so it's just the bigger the better in general. Don't get a capacitor this big, put it on there, you know. Let's see. At what some characteristics of the Boolean sequencer. All right, the history behind it and leading to the characteristics. I'm running out of time already. Skip the history. That's all about me, and you don't care about me. You care about building this thing and understanding it. The characteristics include a long evolving sequence that repeats. Remember, it's made of computer logic hooked up to a computer logic counter. So it implements a truth table, a thing called a truth table, a Carnot map. Okay, if you know what those things are. It steps itself through the very fundamental nature of computer logic called Boolean algebra or Boolean logic and so forth, invented by George Boole way back before computers existed. Okay. Well, so what that means is it has macroscopic patterns, it has medium patterns, and it has microscopic patterns. You'll hear in the short term, you hear it go boopity boop 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 boop, and the next time it'll go boopity boop 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 boop, and the third time it'll go bippity bop bop boop boop boop. You know, like that. Okay. So there'll be the same sequence with a variation on it, repeating, very interesting musically. And then that sequence will evolve over time in a more macroscopic structure and an even more macroscopic structure. You got to hear it. It's really nice, well worth listening to. Experiment with it, make software versions of it. Of course, you can implement it in software. I recommend the programming language Chuck. Just Google CHUCK, Chuck, space Princeton, or Chuck space Stanford. Princeton and Stanford universities have the repositories for the software Chuck. First item come up will be Chuck. Download it. It's a programming language that makes music. That's a whole nother video. Many videos to cover Chuck. I'm going to be busy. But, yeah, out comes the CV. And you can make a little comparator circuit or make a one shot off the clock to give you a, whatever they call that signal, the other companion signal to the CV that pulses once every note. You can do that. Other refinements, running out of time, you can use analog logic. You can clock at audio rates. You can introduce feedback into your logic network to create state information. You can mix. You can use analog CMOS, all kind of crazy gates and state machines and whatnot. You can hook up to it. You can really get wild with it. I'm out of time. I got to go. That's the Boolean sequencer. Give it a try. Makes interesting music. Final thought. Make 2 Boolean sequencers with slightly different logic, and they will dance together and make really interesting sound. Got to go. Less out. Praise the Lord.